Okay. On our previous session, we talked about the one of the multimedia streaming protocol known as the real-time transport protocol, or RTP. We also indicated the functions of RTP. What does RTP do? We know that it is going to focus more on the delivery of a packet, but not on the monitoring of that packet. We know that the RTP will mainly focus on making sure that the packet is delivered. So today we're going to talk about another protocol that works hand in hand with the RTP, which is called the Rtcp. Or the real-time control protocol. So you can see the difference between RTP. This one is what? It's real-time transport protocol. This one is real-time control protocol. So this one is for control. This one is for transport. Okay. Mainly for control. It's going to control the transportation that this RTP is offering. That's why I'm saying they work hand in hand. Okay. Good. Now let's move. So after this lesson, or after knowing about this Rtcp, you will be able to discuss in detail the attributes of the Rtcp. You will identify and describe the features of the Rtcp, which is most or more or less the same as what we did on RTP. We will illustrate the Rtcp header, and we will describe the specification of the Rtcp. What is this Rtcp? As I have already indicated, that Rtcp actually means real-time control protocol. It's mainly used for control. This Rtcp, how does it offer that control? We'll be deep diving in, and we'll be knowing how this Rtcp offers this control. So this Rtcp, they say, is described by the RTP and RFC, which we will know what does this mean. RTP and RFC. We will know what they are actually talking about. So as two basic functions, provide feedback statistics on the quality of service parameters like round trip time. You know what are quality of service parameters, right? Round trip time, delay, jitter, market losses, etc., etc. For the participants to a RTP session. So this RTCP is going to work because of this RTP. So because we will have an RTP session, we're going to need this RTCP for feedback. So the RTCP now we can see that it is used to provide a feedback statistics on the quality of service. You know what is quality of service? How good is the customer receiving the service? It can be you're having two customers. Those customers they can't hear each other, or the network is very bad. So that will be resulted into a bad quality of service. Jitter, delay, packet losses, etc. So the quality of service in an organization differs. Vodacom, for example, will give different quality of services to different customers with different amount of money or with different money that they are paying for the call. So quality of service, it also has to do with cost. How much are you paying? So the more you are paying, the better the quality of service. That's also another thing about this quality of service for your understanding. So this, they say it also carries a canonical endpoint identifier or CNAME to all session participants as the source identifier SSRC may change in case of conflict, and many SSRC can correspond to the same CNAME. I don't even know what they're talking about here, but you can see that they say it carries a CNAME or canonical endpoint to all session participants. Okay, it uses as a port the next highest odd number of the following even number ports of RTP. Okay. But the RTCP traffic must not be above 5% of the RTP traffic in a session. So that's why we say this one RTP is the important one. It's the one that will be, for instance, transporting the video, right? To offer transport to the video. And then this RTCP is going to make sure that that video between the end users is being is actually not having delays, jitter, or if there are delays, this RTCP will then monitor or provide a feedback. So this is just going to provide a feedback. This one will provide a transport. It's more like, let's say we are having a trip to somewhere in a bus or in a train or in a plane. Someone who is actually telling the destination and the source where we are coming from and also where we are going. That the plane now 5 hours behind, or we are 5 hours to reach the destination. So it's more like that. The RTCP is just going to provide the feedback, just going to give us information about the transportation of that RTP session. Okay. So here we talk of this RTP slash RTCP RFC 1889. Okay. A real-time transport protocol RTP is the de facto standard media transport protocol in the internet. So when we talk of media transport, we're talking about transporting an audio or a video. And how is it different from data? How is it different from data? Here, talk of media. We are talking about it can be, if it's an audio, it can be an MP3, right? Video, MP4. So they are different. The data and MP3 file is not the same. So RTCP is for what? It's for this media transport. It will be carrying this audio or video. But RTCP is going to do what? End-to-end monitoring and data delivery and quality of service. So data delivery is going to be about what? It's data now. Something that will be turned down. It's more of information. You know about data. What is data? It's information about something. The collection of when you have data that has meaning, then you're going to have information. So this data is the one that will be transported or delivered so that you can know about the session, what is happening with the session, what is the quality of service about the session. Yeah, good. So here they say RTCP and RTP. RTP and RTCP are commonly built on top of UDP or user datagram protocol. RTP provides some functionality for media transport, but this RTP does not guarantee quality of service, right? And also address resource reservation and also does not perform signaling. These three things, it does not do that. It means the RTCP is the one that will do that. This RTCP is the one that will provide guarantee quality of service, address resource reservation, perform signaling, so on and so forth. You see, this RTCP is going to have what we call ID of sender, provides various report for use in quality of service and congestion control. So on so an app can change resolution or compression strategies, partition size and scaling for what? For conferencing. Okay, so now we talk of this RTCP header. The RTCP header, you now already know what a header is. When we talk of what header, it's going to be something like this. It will like having a description, or they will also indicating the length each and every data that is being placed in the header. So in that header we have version, which is 2 bits, heading 1 bit, and they are the same as for RTP header, right? Both of them. Count 5 bits, the number of reception report blocks contained in this packet. Type, which is 8 bits, and it's what? It's the packet type. The packet type. But length is going to be what? 16 bits, which is the length of the RTCP packet in 32-bit width minus 1, including the header and heading. Okay. So now let's talk of real-time control protocol types. We have sender report, we have a sender report, because you know this RTCP is going to provide feedback, right? This one, it means it's going to be about the sender, right? Statistics from active sender. A receiver report, which is statistic from participant except active send. Because you can have one sender and many receivers, right? But as for one receiver and many senders, that one is rare. It's a rare case. It's not easy to actually monitor that one. But yeah, probably we'll talk about it as time goes. Then source description item, or SDES, includes CNA. Then there's by, which indicates the end of participation, and which is application-specific functions. Okay, these are the types of RTCP, or real-time control protocol types. But this RTCP is a companion control protocol to RTP. As we have indicated, that RTCP is going to work with this RTP. It is more like helping the RTP protocol. But this RTCP is not a signaling protocol. Okay? That is not a signaling protocol as well, and is used to collect end-to-end information. Which means on the previous slide it was a misunderstanding. I misunderstood the previous slide, but I hope you can see it now. It is used to collect end-to-end information about the quality of the session to each participant. But RTCP packets types is going to be as follows. We have already talked about this. We know this. We've already talked about it. They are repeating this. They are repeating that one. Then now let's talk of this sender report, or SR. It's going to have SSRC, which identify the sender, then sender info block, which is going to have network time protocol, NTP, timestamp, send time, and RTP timestamp corresponding to NTP, but informates of RTP data packet timestamp used for intra or and intermedia synchronization. Okay, so I hope you can see this network time protocol timestamp, but NTP timestamp. You know what is timestamp? You know what the use of this timestamp, right? The use of timestamp is when you want to actually be able to assemble the packet at the destination. We use this timestamp. Whenever a packet is being sent, we will know that it has been sent at this time. It must be received at that time. It must be the first one to be received. So we'll send the packet that should be the first one to be received. Then using the timestamp, we'll be able to identify that this one should be the first one to be received. I hope you understand what I'm talking about. Let's say, for instance, we are sending this message. We have 1, 2, 3, 4, 5. So if we send all these packets, what happens if they reach the destination and this number one was received late? Let's say number one was received here. We have the final packet as 3, 1, 4, if the packet was received like this, how will you know that this one must go here? This timestamp also is helpful for that. You can also do uh, you can see sequence number. You can give them a sequence number, right? So timestamping and sequence number, they are helping us for such things. Okay. And then here they say the sender's packet count and octet count. So this sender info block includes 1, 2, 3. Then multiple report blocks. Each block has SSRC and fraction lost, number of lost. Okay. But highest sequence number received inter-arrival jitter, LSR, or DLSR. Let's just read for understanding. Okay, but RTCP, RR, and SDS receiver port. You know, the RR is receiver port. Then this SDS they're saying is what? Source description packet. So similar to SR but without sender information block. Okay. It does not have what information block. It's similar to SR or to sender report, but no information block. RTCP source description packet or SDS contain CNA mandatory. They contain CNAME. I don't know if they mean it's mandatory or what, but a constant for a user, unique among all users, providing binding across multiple media sent by a user. Okay. Example, poly id at utopia.poly.edu 718267. Okay, yeah, this is understandable. The C name, the same, it's more of what? It's unique among all users. So it means it's the one that will help this RTCP identify the user, right? Okay. Let's continue with the sender report, which is going to do what carries statistic from active senders, right? We have this header like something. It's a header you can see. So in this case, they say the phishing where V is equal to 2 and P. I don't think they can ask you to draw this. If they ask you to enter the screen, I don't think they can ask. NTP timestamp. We were already talking about this thing. Okay. So this is another repetition of what we were talking about behind the SR packet or sender port packet, then receiver port packet. The difference, they say there's no information here. Let's see what the information is. Um, okay, I can't see the difference between the two, but you can go and check the difference if it's needed that you must know. But the receiver port, again, you can see it's like this. It's not like a direct. Okay. For SRC identifier allocation. Now we talk of SRC, and but the SSRC identifier carried in the RTP header and in various fields of RTCP packets is a random 32-bit number that is required to be globally unique within an RTP session. All RTP implementations must be prepared to detect collision and take appropriate actions to resolve them. If a source discovers at any time that another source is using the same SSRC identifier as its own, it must send an RTCP by packet for the old identifier and choose another random one. Okay, this is understandable. But if a receiver discovers that two other sources are colliding, it may keep the packet from one and discard the packet from the other. Okay. Okay, this is understandable. Very understandable. But now this what we call source description. This is what we're talking about. Yeah. Source description identifier or SDES. So description identifier. It allows the binding of SSRC value within an actual identification of the user. But endpoints need to send an SDES packet at the beginning of the session. By ends a user participation in a call, app application specific RTP packet. Okay. So here they're saying there's also another one which is SDES from this SSRC, which allow the binding of SSRC and actual identification. So this is the SDES packet. And this is a RTCP by packet. RTCP by packet. So as you can see, this is the main focus on this slide, the RTCP, which they're saying synchronize across different media streams. Provide feedback on the quality of data using lost packet counts. Identify and keep track of participants with transmission requests, so on and so forth. So you can understand why is it doing this. Provide feedback on the quality of data using lost packet counts. So if there are a lot of packets that have been lost, it means it will tell us that the quality of service is very low. Or to tell us the feedback. Do we have a we have high loss of packets. So you can see how this RTCP looks like, where it is, the traffic layer. So this RTCP is RTP control protocol. I hope you can see. It's more like real-time transport protocol control protocol. That's what they're saying. But critically transmit report to all participants. Function of Functions of RTCP provide quality of service feedback. We're repeating this uh, for many times now. But carry persistent ID or canonical name or CNAME. Track a user if SSRC changed, confliction, etc. That associate multiple streams from a user A and B, and control the rate of RTCP packet scalability, or convey minimal session control information. Okay, but not enough for complicated. Okay, that's enough. But then we have what you call RTCP compound packets. So these RTCP packets have a length field in the header aligned to 32 bits, stackable, and sent in a compound packet of at least two RTCP packets, for example. Okay, example is this one. But if encrypted a random 32-bit integer packet, you can see with source report and source SDES, you can see here, then they say by SSRS, SSRC. Yeah. Okay. Good. Now let's talk about some issues in RTP and RTCP. How often should RTP report to exchange? Must be able to provide real time and with enough resolution for quality of service interpretation. Fixed bandwidth, okay, as proportion to channel bandwidth. How to use the RTCP reports, reroute, end-to-end quality of service information may not be sufficient. Okay? But application adaptation, that's another issue. Hopefully we will understand this as we continue. But the RTCP or round trip time calculation, RTCP for round trip time calculation, these are going to do round trip time. Left sender at T1, receiver at T2. There is what we call DLSR. DLSR. Where here we have T1, T2, T3, T4. So to calculate the round trip time, you can see this IR packet contains NTP, which is equal to T1. The RR packet contains last SR timestamp LSR T1 delay since last SR or DLSR T2 minus T3. Then round trip time, which is equal to what? T4 minus T3 plus T2 minus. And that's just simple mathematics. I hope you can be able to see here. Because this DLSR is T3 minus T2, right? So round trip time is T4 minus T3 plus T2 minus T1, and then so on and so forth. So doing that, you can be able to get here. Okay. Activity transmission interval. RTP is designed to allow an application to scale automatically over session sizes ranging from a few participants to thousands. In an audio conference, the data I mean, the data traffic is inherently self-limiting because only one or two people will speak at a time. Okay. So with the multicast distribution, the data rate on any given link remains relatively constant, independent of the number of participants. However, the control traffic is not self-limiting. If the reception reports from each participant were sent at a constant rate, control traffic will flow linearly with the number of participants. Okay. But to maintain scalability, the average interval between packets from a session participant should scale with the group size. The control traffic should be limited to a small and known fraction of the session bandwidth. Small so that the primary function of the transport protocol to kill data is not right. Known so that each participant can independently calculate